A new study has confirmed that the Earth is made out of the same elements as the Sun, but has less of the volatile elements, such as hydrogen, helium, oxygen, and nitrogen. The findings, reported in the journal Icarus and on the pre-press physics website archive.org, are part of a new project designed to measure the elemental composition of other stars and the terrestrial exoplanets orbiting around them. One of the study's authors, Associate Professor Charlie Lineweaver from the Australian National University, says the composition of a rocky planet is one of the most important missing pieces in science's efforts to determine if a planet is habitable. Lineweaver says every star has some kind of planetary system in orbit around it, and the majority of stars probably have rocky planets in or near their habitable zones. That is the Goldilocks area around a star where it's not too hot and not too cold, but just right for liquid water, essential for life as we know it, to pool on the surface. And just like the Earth, other terrestrial worlds are also devolatilized pieces of their host stars. You see, stars and the planets orbiting around them form at the same time through the same gravitational collapse of a molecular gas and dust cloud. The centers of these molecular clouds are cold, dark, and dense, containing hundreds to millions of times the mass of the Sun. The collapse can be triggered by a range of events, including overdensities caused by gravitational interactions with large bodies or structures, by black holes, or by shock waves from nearby supernovae, as was the case for the formation of the Sun and its solar system of planets, moons, asteroids, comets, and meteoroids 4.6 billion years ago. As gravity pulls material in the collapsing cloud closer together, the center of the cloud gets more and more compressed and hotter. Depending on the mass of the collapsing molecular cloud, hundreds to thousands of hot overdense regions can form, each with the potential to become the core of a newborn star. As the molecular cloud continues to collapse, it fragments into smaller superdense regions, which eventually further contract to each form a protostellar core. Around each of these protostellar cores, inherent motions within the collapsing cloud causes the cloud to churn and begin rotating in the same direction. The protostar continues to accrete material from the surrounding stellar nebula, increasing in density and mass, and therefore gravity, which causes further contraction. The conservation of angular momentum produced by the spinning protostar's contraction causes it to increase its rotation rate, while at the same time the ongoing accretion of surrounding material causes its core pressure and temperature to further increase. Eventually, the core pressure and temperature of the contracting protostar increases to the point where nuclear fusion begins, as hydrogen atoms are forced together, forming helium atoms, releasing huge amounts of energy in the process, and the newborn star begins to shine. For about 90% of its life, the star will continue to burn hydrogen into helium, a period in its evolution known as the main sequence. Meanwhile, at the same time as all this is happening at the center, the rotating cloud surrounding the protostar begins to flatten out into a disk and gets thinner and thinner as it spins, sort of like a spinning clump of dough flattening out into the shape of a pizza. These circumstellar or protoplanetary disks, as they're called, are the birthplaces of planets. As the disk spins, the material within it travels around the star in the same direction. Eventually, the tiny grains of material within the disk will begin sticking together due to electrostatic charges. As these small clumps of material orbit within the disk, they gradually accrete more and more of the surrounding material, growing bigger and bigger in the process. And the bigger these conglomerates become, the more gravity they have, and so the more material they attract, and the bigger they get. Eventually, they form planetesimals, which themselves can then grow big enough to become planets. Different materials condense out of the protoplanetary disk at different distances from the protostar, depending on temperature. Metals such as iron, nickel, and aluminum, together with rocky materials such as silicon, will condense out closer to the star than volatile compounds such as water, ammonia, methane, carbon dioxide, and carbon monoxide, which can condense out into solid ice grains beyond the so-called snow line. Therefore, the inner regions of these circumstellar or protoplanetary disks usually contain mostly rocky material, as much of the original gas is likely being gobbled up and cleared out by the developing star. All this leads to the formation of smaller rocky planetesimals close into the star. In the outer part of the disk, though, more gas remains, as well as ices that haven't been vaporized by the growing star. This additional material allows planetesimals further out from the star to gather more material, eventually evolving into gas and ice giants. The authors conducted their study by comparing the composition of Earth rocks with meteorites and with the Sun's outer atmosphere. This comparison yields a wealth of information about the way the Earth formed.